Hello, this is the second half of simple linear regression, where we actually do the hypothesis test and determine how strong our model is and if we can use it for prediction. This is kind of the easiest half, so if the other half sank in, we're all in good shape, I think. Anyway, so in Word, I've already got, I'm sorry, the dog has decided to bark. In Word, I've already got the notes pulled up. This was section 13.7, and I think it's on page 7 of the handout that I left in Blackboard for you. So you should already have the regression run. We don't have to do anything else in Excel. This is our simple regression analysis model run from PHStat. If you had run it in Excel, you'd have gotten something that looked very similar. At the top of the model is our regression statistics, and it's got, for instance, the number of observations, the R square, which we're going to talk about a little bit later, and then something called multiple R. This is the correlation coefficient between the two variables. It has an ANOVA table, just like our analysis of variance did, and it has the p-value out here on the end, on the other half of the F statistic. And down below that, there's something called a coefficients table that has more p-values, and it has some coefficients in it that we're going to look at. So you should have, if you ran it, you should have saved the file, and you'd be able to get your output. So the first thing we want to do is we've done all the preliminary work. We've done our residual analysis. We don't think we have a problem using regression. So the next thing is to look at our first hypothesis test, which is a test for the slope of the line. You remember when we started talking about regression and the relationship between these two variables, we said that if there was no relationship, they should have a slope of 0. In other words, it just looks like a horizontal, mass of points with no up or down to it. So when we do our hypothesis, we write our null hypothesis as a slope, which we call B1 equals 0, which says that there's no significant linear relationship. And then our alternative is that our slope is not equal to 0. And this suggests there is a significant linear relationship. The place you get your p-value from is up here in your regression statistics. Here under significance F, that's a p-value in your ANOVA table. And you remember we said that if we had 0.000, we would write it as, p is less than or equal to 0.001. So just put a 1 at that last decimal that they show there. So our decision rule, of course, is that we're going to reject our null hypothesis if the p-value is less than alpha. That rule never changes. And since our p-value is so small, our decision is to reject our null hypothesis. And the explanation for this is that there is a significant linear relationship between sales and profiled customers, which is what you want to hear if you've just run a regression. The next thing you want to look at is you want to determine how much of the variability in your sales, your dependent variable, is explained by the presence of the independent variable, your X. In other words, how much of the sales is explained by the number of profiled customers within a small geographic radius. The R square is used in this assessment. So you look up in the same printout, you look in the regression statistics, and here's my R square row. And you'll see your R square is 0.8479. As a matter of fact, if you took your correlation and squared it, you would come up with this 0.8479. As long as you're doing single linear regression, you use the R square. If you're using multiple regression, in other words, you got more than one independent variable, then you would switch over to this adjusted R square. Anyway, so my R square is 84.7%. And what this tells me is that the presence of the profiled customers, the size of that population, explains about 84.79% of the variability in the sales. Now, your determination of what this means is really a judgment call. Obviously, the more variability that is explained, the more useful the model is going to be for prediction. So you want a high number. I think this number is abnormally high compared to the kinds of R-squares that I have seen in the research that I have done over the years. Usually they're not that high in a single regression model. So, my assessment of this would be the R-square is really, pretty good. It's fairly high, and I think this would be a very useful model in doing prediction. And then once you've decided this, by the way, there's no cutoff for this, number. So you can't say over 50% or 60% or 80%. It's just whatever you're going to be using this model for and what you're comfortable with. So assuming that we're comfortable with 84.79%, then we would start to think of using this regression equation to predict. The regression equation itself is up in our regression output, and it's in the coefficients table and these two numbers. So the one that says intercept, this is just a formula for a straight line. So the y-intercept is a negative 1.2088, and the profile customers, this is my x, I'm sorry, my slope that goes with my x is 2.0742. So when I write my regression equation, I would say, y equals my predicted y is going to equal my b sub o, which is the intercept, plus the slope, which was the other number in the table, times the x value. So it ends up being negative 1.2079 plus 2.074 x1. Suppose we want to predict sales. If there are 5 million profiled customers within 30 minutes of the sunflower store, I would just substitute my 5 into this equation and solve. And it turns out that, I would predict I would have sales of $9.16 million if I had that many profiled customers within that geographic area. Be very careful. Up here, I almost forgot it. Something called interpolation versus extrapolation. You should never predict a value for y, your dependent variable, using values that are outside the range of the independent variable that you use to build your model with. So if you went back and looked at your initial data, here it is, there's my data up here. You'll see my profiled customers. It looks like the smallest number I see there is 2.2 million, and the largest number that I see there is 5.8 million maybe. So I'm comfortable making a prediction anywhere within, this range of values that I use to build my model with. The thing is that you do not know what happens to this model once you get over on each end. So if I go, say, 6 million, I don't know. This model, maybe it suddenly becomes curvilinear somehow. I don't know what happens when it's below 2 million. Maybe it's curvilinear somehow. So be safe rather than sorry, and do not make predictions outside that range that you used to build your original model with. Also, be very careful. There's always error in linear regression models. So when you use them for prediction, you should not expect to have sales of exactly $9.16 million. You've got a pretty strong R square, so it should be fairly close, but it's not going to be exact. And that really is the rest of it. I did leave, in case anybody has an interest, the calculations for the regression equation, all figured out in an Excel spreadsheet, and how to do these other calculations by hand. But if you're using PHStat, you should not need to do any of this by hand. So I think, you'd want to finish up your problems once you've done your residual analysis by doing your hypothesis test for the slope. Then you would want to look at your R square, and then you want to do the prediction if they ask you to do it. I don't see a mistake there. Okay, so that's the end of this one. Thank you.